In the heart of ancient Greece, over 2,000 years ago, a brilliant mind pondered the mysteries of the universe. That mind belonged to Aristotle, a philosopher whose ideas shaped science, logic, and mathematics for centuries to come. Aristotle lived in a world of marble temples, bustling marketplaces, and lively debates. His curiosity led him to question not just the nature of life, but the very foundations of mathematics and motion. Among his many puzzles, one stands out for its elegance and enduring mystery: the wheel paradox. This paradox, first described in the 4th century BCE, continues to fascinate mathematicians and philosophers to this day. But what exactly is Aristotle's wheel paradox? Let's break it down step by step. Imagine two wheels, one large, one small, rigidly attached together along the same axis, like two concentric circles sharing a center. The wheels are rolled along a straight path, so that both touch the ground as they move forward. At first glance, intuition tells us that the larger wheel, with its greater circumference, should trace a longer path on the ground than the smaller wheel. After all, a bigger circle means a longer journey, right? But here's where the paradox emerges. As the wheels roll together, both complete exactly one full rotation. That means the point of contact for each wheel travels the same distance along the ground. So if both wheels rotate once and both touch the ground, how can the smaller wheel's path be as long as the larger wheel's? This seems to defy the basic rules of geometry. Mathematically, the length traced by a full rotation of a wheel is its circumference, given by the formula c equals 2πr, where r is the radius. For different radii, the circumferences are different. So how can both wheels cover the same ground? The answer lies in the geometry of rolling without slipping. When the wheels are fixed together, the smaller wheel's outer edge never actually touches the ground. Its path is virtual, a trace in the air, not on the surface. Only the larger wheel's circumference makes contact with the ground, dictating the distance traveled. The smaller wheel, though it rotates once, does not leave a continuous track. This subtle distinction is the heart of the paradox. If you were to paint a line on the outer edge of each wheel, only the larger wheel's paint would mark the ground. The smaller wheel's paint would hover above, tracing an invisible arc. Philosophers and mathematicians have debated this puzzle for centuries. Some argued it revealed flaws in the ancient understanding of motion and continuity. Others saw it as a lesson in the dangers of unchecked intuition. In the 19th century, mathematicians like Augustin Cauchy and Carl Weierstrass developed rigorous definitions of continuity and limits, helping to resolve the paradox mathematically. Today, we understand that the paradox arises from confusing the physical path traced on the ground with the abstract path traced by the smaller wheel's edge. The two are not the same, even though the wheels rotate together. Real-world analogies help clarify this. Imagine a train with wheels of different sizes fixed on the same axle. Only the larger wheel's rim touches the rail, while the smaller wheel spins in the air, never leaving a mark. The paradox also invites us to reflect on the nature of abstraction in mathematics. Sometimes our mental models, though elegant, can mislead us when applied to the real world. Aristotle's wheel paradox reminds us to question our assumptions, to look deeper than surface appearances, and to appreciate the subtlety of mathematical truth. In the end, this ancient puzzle is more than a curiosity. It's a powerful illustration of how science and philosophy evolve together, challenging us to think critically and creatively about the world around us.